We've got some unfinished business to take care of today. In a previous video we attempted a preparation of potassium permanganate, a very useful oxidizing agent. We managed to get a very intense purple solution which obviously contained a lot of permanganate, but no actual solid product. So today we're going to try again, but using a variation on the reaction with a different oxidizing agent. Let's go through our three key reactants. First up, manganese dioxide powder. This is very black colored even for manganese dioxide, and it's an old sample, so we suspect it probably also contains some other manganese oxides as well. We're going to be using 10 grams for the reaction. Next up, our oxidizing agent. In the previous video we used potassium nitrate. This time we're going to use something a bit stronger, potassium chlorate. Here we've got 14.1 grams of potassium chlorate crystals, which is a 50% excess on what we theoretically need, so this should hopefully give plenty of oxidizing power. And finally, potassium hydroxide, which is our alkali and will form the potassium salt of our product. We're using 12.9 grams, which is the stoichiometrically correct quantity. As a reminder, here's the balanced equations for what we're going to be doing. This explains the quantities of reactants we just went over. First thing we've got to do is crush up the chlorate and manganese dioxide up into a nice homogeneous powder as finely as we can. This is looking pretty good, so let's give it a go. We'll add this to the potassium hydroxide. The theory is that this should melt first and so form a homogeneous mixture in the reaction vessel. We'll give it a mix. For the reaction vessel we're going to use a stainless steel cup. Our steel food shaker has been obliterated. That's what happens when you produce cyanide in metal containers. So we're ready to rock. We'll apply a fairly gentle flame to start with. Within seconds we've got a reaction. You might already know, but manganese dioxide is a good catalyst for the decomposition of potassium chlorates, and so on heating it's going to rapidly melt and give off oxygen gas. The mixture melts and becomes nice and homogeneous with some stirring. The bubbling dies down and the liquid is replaced with a dark-colored solid product. We heated for another 30 seconds and then switched off the heat. The contents of the pot crackle as it cools down. Well, that was quick. Way quicker than the previous experiment using potassium nitrate. You can see on our stirring spoon that we've got an intense blue-green color in there. That purple color suggests that we're on the money. We're going to extract the contents of the pot using 40 ml of water. It breaks up pretty easily. Now we'll get the contents into a beaker. We're going to get all the solids dissolved as much as possible by using a microwave to heat. Great. And now it's time to filter the hot mixture. We wash out the beaker and wash the precipitate with another 10 ml of so of hot water. Okay, here's the liquid. Don't put away your filter equipment yet. You're going to be needing it again. This solution contains potassium manganate. To convert this to potassium permanganate, one clean method is to use carbon dioxide gas. So here's a little simple CO2 gas generation setup. We've got sodium bicarbonate in the flask, and this is stoppered up but with an adapter leading to a hose and then a glass tube to bubble through our manganate solution. We're not sure how much we need to use, but we can top up the flask if we need to. Here's dilute hydrochloric acid. We'll add some and then quickly restopper the flask in order to generate our CO2 gas. The color in the mixture almost immediately changes to red, and there's a precipitate appearing in the mixture. We add fresh batches of acid and keep the bubbling going strongly for a couple of minutes. The end result looks like a bit of a mess. A dark red colored mixture with a heavy precipitate. We gave this a quick blast to warm it up. And now we're going to filter again to remove the precipitate. The precipitate is brown manganese dioxide, formed in the disproportionation reaction. The filtrate is now an intense purple color. The color of permanganate in aqueous solution. We washed the brown precipitate with 5 ml of hot water. And here's the filtrate. We figured we'd first chill this down to see if we could get any crystals of product forming. So we covered in wrap and then placed the beaker in the freezer for about an hour. At this stage you'll need to do a bit of a cleanup of your work surface and glassware. Permanganate reacts with lots of materials including anything organic to produce a brown stain of manganese dioxide. Luckily it's easy to remove. Here's a little bit of sodium bisulfite in a beaker, and we'll get this into a solution with some water. Very useful to have around when you're dealing with permanganate and manganese dioxide. Here's the beaker from the freezer. We've got a whole lead more manganese dioxide precipitating out, and that red color forming again. Looks like the disproportionation reaction actually takes a while to complete fully. So let's heat this up and make sure that any soluble is dissolved. And we filter once again. Look at that color. So we'll repeat the process and chill the filtrate down again in the freezer for a few hours to see what happens. Here's the result. The mixture is still purple, so there doesn't seem to be much more manganese dioxide forming. But there is a small amount of a crystalline dark solid. So let's filter this off and check it out. We let it dry as thoroughly as we could. Well, here we go. The filtrate is still very strongly colored, but we've also got a crystalline solid, as you can see. It's slightly brown colored, so it probably does have some manganese dioxide in there still, but it is the right very tiny, almost black crystals in order to be solid potassium permanganate. But it's only 1.6 grams, which if pure would be a 13% yield on the starting manganese dioxide. Not spectacular. So let's do a couple of quick tests. Firstly, let's add the tiniest amount of the crystalline product to a beaker of water. Only a tiny trace of crystals on the spatula. But it still forms a purple-colored solution. The classic permanganate intense coloration. Permanganate is a strong oxidizing agent, and in contact with some organic materials can spontaneously ignite. Let's try the product with a drop of liquid glycerin. That's pretty fast, but there's no flame generated. So our product is relatively pure, but it's probably still a bit damp. So there we go. We finally did it in the end. Solid potassium permanganate crystals. It's not a very efficient reaction, however, and there's a lot of leftover manganese dioxide which could in theory be recycled. The remaining filtrate could probably also be evaporated and concentrated down in order to give more permanganate crystals though. So we'll guess that you can achieve a maximum yield of around 25% using this method, but it's going to be a lot of messy work. In reality, potassium permanganate is fairly easily obtained, so you would need to be fairly desperate to go down this path. We'll leave you there. We've got a few more videos in this festive sequence lined up, so we're not quite finished yet. Stay tuned for more festive reactions.